Hello there, and welcome. I'm so glad you found your way here tonight. Maybe you had a long day, or maybe you're the kind of person who likes falling asleep to deep thoughts and quiet wonders rather than counting sheep. Either way, this journey is for you. You've got nothing to do but rest. Let your mind relax, your breathing slow, and your body grow light, as if gravity itself has softened just for this moment. Because tonight, we're not simply stargazing. We're drifting toward the moon, that pale, ancient companion that has watched over the earth for longer than any creature has drawn breath. It rises and sets, waxes and wanes, pulls the tides and stirs the poets. And yet beneath its soft silver glow lies a world of secrets. Craters older than dinosaurs, mountains taller than any on earth, and shadows that have never once seen sunlight. We'll travel gently across its silent surface, from the dark Maria to the bright highlands, from the footprints of astronauts to the mysteries we still cannot explain. Some of what you hear tonight may surprise you. Other facts might simply drift past like clouds across a quiet sky, soft, curious, and easy to forget by morning. And that's perfectly fine. This is not a test. There's nothing you need to remember. Just let the words wash over you like moonlight through a window. If these calm, curious explorations help you unwind or give you a quiet way to end your day, consider liking and subscribing. It helps others find their way here too, one sleepy soul at a time. But for now, let yourself settle. Take a breath, and let's begin. The moon is slowly drifting away from Earth. Every year, our lunar companion moves about 3.8 centimeters farther into space. It's not much, barely the width of a few coins. But over millions of years, this quiet retreat adds up. When the moon first formed, it hung much closer to our world, looming large in the prehistoric sky, pulling monstrous tides across ancient shores. Back then, a day on Earth was only 6 hours long. The moon's gravity has been slowing us down ever since, stretching our days longer and longer as it inches away. One day, billions of years from now, the moon will be so distant it will no longer be able to cause a total solar eclipse. The geometry simply won't work. But that is a story for a far-off future. For now, the moon remains close, faithful, and bright. And tonight, it's still watching over you. The moon was likely born from a violent collision. About 4.5 billion years ago, something the size of Mars slammed into the young Earth. The impact was catastrophic beyond imagination. Rock, magma, and debris exploded outward into space, forming a glowing ring around our wounded planet. Over time, this debris coalesced, cooled, and formed the moon. Scientists call this the giant impact hypothesis, and while it's not proven with absolute certainty, it remains the most widely accepted explanation for how our moon came to be. The moon, then, is not a stranger. It is a child of Earth, made from the same ancient material, shaped by the same primordial violence. When you look up at the moon, you are looking at a piece of home, flung into the sky long before life even began. In a way, we are all made of moon dust and ancient starlight. The moon has no atmosphere to speak of. Unlike Earth, which is wrapped in a blanket of air that carries sound and warmth and weather, the moon is exposed. There is no wind, no clouds, no rain. A flag planted on its surface will never flutter in a breeze. Footprints left by astronauts will remain undisturbed for millions of years, preserved in the fine, lunar dust like fossils in stone. The silence there is absolute, No birds, no rustling leaves, no distant hum of civilization. Just stillness. And in that stillness, the stars shine without twinkling, steady and sharp against the endless black. It is a quiet so deep it's almost sacred, a place where time itself seems to hold its breath, waiting for something that may never come. The dark patches on the moon are ancient lava plains. For centuries, people imagined they were seas. The early astronomers called them Maria, the Latin word for seas, and the names remain to this day. The Sea of Tranquility, the Ocean of Storms, the Sea of Serenity, the Sea of Crises. But they hold no water. They never did. These vast, dark regions are the scars of ancient volcanic eruptions, places where molten rock once flooded the surface and cooled into smooth basalt plains. The eruptions ended billions of years ago. The moon's interior cooled, its volcanoes fell silent, and the Maria became still. Now they rest like frozen oceans reflecting sunlight, just a little less than the brighter highlands, giving the moon its familiar face, its pattern of light and shadow that humans have gazed upon since the very first eyes looked upward and wondered what was out there. The moon is the 5th largest moon in the solar system. It may seem modest compared to Jupiter's giant Ganymede or Saturn's hazy Titan, but our moon is remarkably large for its host planet. Relative to Earth, the moon is enormous. No other planet in the inner solar system has a moon anywhere near this proportion. Mercury and Venus have no moons at all. Mars has only 2 tiny captured asteroids. Some scientists even consider the Earth-Moon system a double planet, 2 worlds locked in a gravitational embrace, spinning together through the cosmos. This unusual relationship may have helped stabilize Earth's tilt over billions of years, keeping our seasons relatively mild and our climate more predictable. The moon is not just a companion. It may be one of the reasons life on Earth was able to flourish at all. Gravity on the moon is about 1/6 of Earth's. If you weigh 180 pounds here, you would weigh only 30 pounds on the lunar surface. You could jump 6 times higher, lift boulders that would be impossible to budge on Earth, and bound across the regolith in long, floating leaps. The Apollo astronauts discovered this firsthand. Walking on the moon was unlike anything they had ever experienced. Every step was a slow-motion ballet, every fall a gentle tumble into the dust. It was disorienting at first, but also joyful. They laughed as they hopped across the surface, kicking up particles that hung in the air for impossibly long moments before settling. In that reduced gravity, even the heaviest burdens became light. The moon, it turns out, is a place where you can almost float. The moon's surface is covered in a layer of fine dust called regolith. It's not like the soil we know on Earth. There's no organic matter, no moisture, no softness to it. Regolith is sharp and abrasive, made of tiny glass beads and jagged rock fragments created by billions of years of micrometeorite impacts. It clings to everything. It scratches visors, clogs joints, and works its way into the smallest crevices of equipment. The Apollo astronauts called it a nuisance, and some even developed allergic reactions after breathing it inside their spacecraft. It smelled faintly of gunpowder, they said, a sharp, burnt smell that lingered in the cabin. And yet, this same dust holds clues to the moon's past. Every grain is a record of impacts, solar wind, and cosmic radiation. The regolith remembers what the moon has endured. The moon has mountains taller than any on Earth's continents, The highest peaks near the lunar South Pole rise more than 10 kilometers above the surrounding terrain. That's taller than Mount Everest by a considerable margin. But because there is no atmosphere, no erosion, no weather to wear them down, these mountains remain sharp and ancient, frozen in time since the earliest days of the solar system. Their slopes have never known rain. Their summits have never felt wind. They stand in perfect silence, casting long shadows across craters that have not changed in billions of years. If you could stand on one of these peaks and look out across the moonscape, you would see a world utterly still, utterly untouched, utterly alien, and yet somehow also familiar. The far side of the moon is not the dark side. It receives just as much sunlight as the side that faces Earth. The confusion comes from the fact that we never see it from our vantage point. The moon is tidally locked, meaning it rotates exactly once for every orbit around Earth, always showing us the same familiar face. The far side remained a mystery until 1959, when the Soviet spacecraft Luna 3 sent back the first blurry images. What scientists found surprised them deeply. The far side is dramatically different from the near side. It has almost no Maria, those dark lava plains that give our moon its face. Instead, it is heavily cratered, rugged, and ancient, covered in highlands that stretch unbroken from horizon to horizon. No one knows exactly why the two hemispheres are so different. The moon, even after all this time, still holds secrets it has not revealed. There is water ice hidden in the moon's permanently shadowed craters. Near the poles, where sunlight never reaches, temperatures plunge to minus 250 degrees Celsius. In these frozen pits, ice has survived for billions of years, shielded from the sun's relentless heat. It arrived on comets and asteroids long ago, and it stayed, locked in the cold and the dark, waiting. This discovery has changed how we think about the moon. Water is not just a scientific curiosity, it is a resource. Future astronauts could use it for drinking, for growing food, for splitting into hydrogen and oxygen to make rocket fuel. The moon is no longer a barren wasteland in our imagination. It is a place with potential, a stepping stone to the deeper reaches of space, a way station for travelers heading to Mars and beyond. Moonquakes are real, and they can last for hours. Unlike earthquakes, which typically subside within minutes, moonquakes can rumble on and on, their vibrations echoing through the rigid lunar crust. The longest recorded moonquake lasted more than 10 minutes, with aftershocks continuing for hours afterward. This happens because the moon is dry and rigid, with no water or soft sediment to absorb seismic energy. Once the moon starts trembling, it rings like a bell, slowly fading into stillness. The Apollo missions left seismometers on the surface, and for years, scientists listened to the moon's quiet groans and shifts. It is not a dead world. It still stirs, still adjusts, still echoes with the memory of ancient forces deep within its core. The moon has a very thin exosphere. It's not quite an atmosphere, not in any meaningful sense that we would recognize. But there are trace amounts of gas clinging to the surface, atoms of helium, neon, argon, and other elements released by the solar wind or escaping from the interior. This ghostly envelope is so thin it's almost indistinguishable from the vacuum of space. Yet it exists. It drifts and shifts with the moon's day and night cycle, thickening ever so slightly in the cold of lunar night, thinning in the blaze of day. It is the faintest whisper of an atmosphere, barely there, yet not entirely absent. The moon is not completely naked after all. It wears the thinnest veil, invisible to all but the most sensitive instruments. The moon influences Earth's tides more than the sun does. Even though the sun is vastly more massive, the moon is so much closer that its gravitational pull dominates the ocean's ancient rhythm. Twice a day, the seas rise and fall in response to the moon's position overhead. High tides swell where the moon's gravity is strongest, and again on the opposite side of Earth, where the planet itself is pulled slightly away from the water. This tidal dance has been going on for billions of years. It shaped coastlines, carved estuaries, and created the intertidal zones where some of the first complex life emerged from the water and learned to breathe air. The moon's pull is gentle but persistent. It has been sculpting Earth since the very beginning of our world. Only 12 humans have ever walked on the moon. All of them were American astronauts, all of them were men, and all of them traveled there between 1969 and 1972 during NASA's Apollo program. Since then, no human being has returned to the lunar surface. The footprints they left behind are still there, undisturbed in the fine gray dust. Their flags still stand, though the fabric has long since been bleached white by decades of unfiltered solar radiation. For a brief moment in history, humanity reached beyond its cradle and touched another world. And then, for reasons political, financial, and practical, we stopped. We turned away. But the moon waits. It has always waited. And perhaps before too long, new footprints will join the old ones. The moon has no global magnetic field to protect it. Earth's molten iron core generates a powerful magnetic shield that deflects the sun's radiation and protects life on the surface. The moon has no such protection. Its core cooled long ago, and any magnetic field it once possessed faded into silence eons before the dinosaurs walked the Earth. Without this invisible shield, the lunar surface is bombarded constantly by solar wind, cosmic rays, and high-energy particles from deep space. This radiation is dangerous to humans and damaging to electronics. Future lunar bases will need to be built underground or shielded with thick layers of regolith to protect their inhabitants. The moon offers no shelter from the cosmos. It is a world fully exposed, standing bare and vulnerable beneath the stars. A day on the moon lasts about 29.5 Earth days. That means roughly 2 weeks of continuous, relentless sunlight, followed by 2 weeks of unbroken darkness. During the lunar day, temperatures on the surface can soar to 127 degrees Celsius, hot enough to boil water if there were any. During the lunar night, they can plummet to minus 173 degrees, colder than any place on Earth. This extreme swing happens because there is no atmosphere to hold heat or distribute it evenly. The moment the sun sets, the warmth radiates away into the void of space. The ground cools rapidly and the long, cold night begins. For any future settlers, managing this cycle will be one of the greatest challenges. The moon does not offer the gentle rhythms of Earth. It demands adaptation, endurance, and patience beyond anything we have known. The moon appears larger on the horizon because of an optical illusion. When the moon is low in the sky, your brain compares it to trees, buildings, mountains, and other objects on the horizon, making it seem enormous, swollen, almost close enough to touch. When it's high overhead, there's nothing nearby to compare it to, and it appears smaller, more distant. The actual size of the moon in the sky doesn't change at all. It's the same disk whether rising, setting, or at its zenith. This illusion has puzzled humans for millennia. Ancient philosophers debated its cause, and even today, scientists aren't entirely sure why our brains perceive it this way. But the effect is undeniable. A full moon rising over a distant hill, glowing amber through the atmosphere, is one of the most beautiful sights the natural world offers. The moon's craters are named after scientists, explorers, philosophers, and artists. There is a crater named Copernicus, after the astronomer who placed the sun at the center of the solar system. There is Tycho, named for the Danish observer who mapped the stars with astonishing precision before the telescope was even invented. There's even a crater named for the composer Johann Sebastian Bach, and others for Aristotle, Plato, and dozens of other luminaries from human history. These names were chosen by the International Astronomical Union, the body responsible for naming celestial features throughout the solar system. The tradition began centuries ago and continues today. When you look at the moon through a telescope, you are reading a map of human achievement, a gallery of the minds who dared to wonder about the universe and left their names etched in stone and shadow for all eternity. The moon is slowly shrinking. As its interior continues to cool over billions of years, the moon contracts, wrinkling like a grape, slowly turning into a raisin. The shrinkage creates features called Lobat scarps, long curved cliffs that snake across the surface for many kilometers. Some of these scarps are relatively young in geological terms, forming within the last few 100 million years. The shrinkage also causes moonquakes as the crust cracks and shifts under the stress of contraction. The moon is not static. It is still changing, still adjusting, still settling into its final form. Even worlds that seem frozen in time are quietly transforming, measured not in years or centuries, but in the slow, patient rhythm of deep geological time. The moon has been struck by countless asteroids and comets throughout its long history. Every crater you see is a scar from an ancient impact, a record of violence preserved for billions of years. Some craters are small, just a few meters across, made by pebbles that struck at tremendous speed. Others are enormous basins, hundreds of kilometers wide, carved by objects the size of mountains. The largest, the South Pole Aitken Basin, is one of the biggest impact craters in the entire solar system. It stretches nearly 2,500 kilometers across and plunges more than 8 kilometers deep into the lunar crust. The moon has no atmosphere to burn up incoming debris, no weather to erase the evidence. Every impact is preserved forever, recorded in stone. The moon is a museum of violence, a chronicle of the solar system's turbulent and chaotic past. The moon's gravity creates a slight bulge in Earth's shape. Our planet is not a perfect sphere. It's flattened at the poles and bulges slightly at the equator due to its rotation. But the moon's gravitational pull adds another subtle distortion, stretching Earth very slightly toward and away from the moon at all times. This effect is tiny, only a few centimeters, but it's measurable with modern instruments. The solid rock of Earth's crust actually rises and falls twice a day, just like the ocean tides, though on a much smaller scale. The moon doesn't just move our water, it moves our entire world, gently kneading the planet beneath our feet in ways we never notice but are always happening. Ancient cultures saw different shapes in the moon's pattern of light and dark. Where Western tradition sees a man in the moon, East Asian cultures often see a rabbit pounding rice or medicine in a mortar. In India, some see hands reaching upward in prayer. In New Zealand, Maori tradition tells of a woman named Rona who was carried to the moon and can still be seen there today. These different interpretations remind us that the same sky can tell different stories depending on who is looking. The moon has been a canvas for human imagination for as long as humans have existed. Every culture has found meaning in its glow, projected their myths and hopes onto its ancient face. The moon belongs to everyone who has ever looked up and wondered. The moon has maskins, or mass concentrations, hidden beneath its surface. These are regions of unusually dense material buried under the Maria, the dark lava plains. They were discovered in the 1960s when spacecraft orbiting the moon experienced unexpected gravitational tugs as they passed over certain areas. The extra mass pulled on them, speeding them up slightly and altering their orbits in measurable ways. Scientists believe mass cons formed when dense lava flooded ancient impact basins and solidified, creating pockets of heavier rock beneath the surface. These hidden dense spots are a reminder that the moon's interior is not uniform. It has structure, history, and complexity that we're still working to understand. The moon is geologically dead, but it wasn't always this way. Billions of years ago, the moon was a violent world. Volcanoes erupted across its surface, flooding vast regions with molten rock. Its interior churned with heat from its formation and from radioactive decay. But the moon is small, and small bodies cool faster than large ones. Over time, the heat radiated away into space. The volcanoes fell silent, and the interior solidified. The last volcanic activity on the moon may have occurred around 1 billion years ago, perhaps even more recently in some places. Now the moon is quiet. Its fires are out. It drifts through space as a frozen relic of its former self, a world that once burned bright but has long since gone cold. Eclipses occur because of a cosmic coincidence. The sun is about 400 times larger than the moon, but it's also about 400 times farther away. This means that from Earth's perspective, they appear almost exactly the same size in the sky. When the moon passes directly between the Earth and the sun, it can block the sun's light almost perfectly, creating a total solar eclipse. This alignment is rare and temporary. As the moon drifts farther from Earth over millions of years, total eclipses will become less and less common, until eventually they stop occurring altogether. We live in a special window of time when the geometry allows for this spectacular event. Future generations may never see a total eclipse. We are lucky to be here now. The moon has a small, iron-rich core. For a long time, scientists weren't sure if the moon had a core at all. But seismic data from the Apollo missions and later studies confirmed that deep inside the moon, there is a dense, partially molten center made mostly of iron. This core is tiny compared to Earth's, only about 300 to 400 kilometers across. It's also much cooler and more solid, which is why the moon no longer has an active magnetic field. The core is a remnant of the moon's fiery past, the last trace of the heat that once powered volcanoes and shaped the surface. Now it sits quietly in the dark, a small heart of iron wrapped in hundreds of kilometers of silent stone. The moon's orbit is not a perfect circle. It follows an elliptical path around Earth, which means its distance from us changes over the course of each month. At its closest point, called perigee, the moon is about 356,000 kilometers away. At its farthest, called apogee, it's about 46,000 kilometers away. When a full moon occurs near perigee, it appears slightly larger and brighter than usual. Some people call this a supermoon, though the difference is subtle enough that most casual observers wouldn't notice. Still, the moon's shifting distance is a reminder that orbits are not static. Everything in space is in motion, constantly adjusting, constantly changing. The first human-made object to reach the moon was the Soviet spacecraft Luna 2, which crash-landed on the surface in 1959. It carried no cameras, no instruments capable of returning data after impact. It simply flew across the void and struck the moon, scattering metal fragments across the regolith. It was a statement as much as a scientific mission, proof that humanity could reach beyond Earth and touch another world. In the years that followed, both the Soviet Union and the United States sent dozens of probes to orbit, photograph, and eventually land on the moon. Each mission taught us something new. Each one brought the moon a little closer to home. The moon reflects only about 12% of the sunlight that hits it. Despite its brilliant appearance in the night sky, the moon is actually quite dark. Its surface is about as reflective as worn asphalt. It only looks bright because it's the largest and closest object in our night sky, and because our eyes are adapted to see well in low light. If you could see the moon up close during the lunar day, you would find it harsh and glaring, with deep black shadows and blinding patches of light. There are no soft gradients, no diffuse glow, just sharp contrasts carved by the absence of atmosphere. Some lunar craters have been named after Apollo astronauts. After the moon landings, the International Astronomical Union honored the 12 moonwalkers by naming small craters near their landing sites after them. Neil Armstrong, Buzz Aldrin, and Michael Collins all have craters bearing their names. So do the astronauts of Apollo 12, 14, 15, 16, and 17. These craters are small, often just a few kilometers across, but they serve as permanent memorials to the humans who made the journey. Long after the flags have faded and the footprints have been buried by micrometeorites, these names will remain, etched into the map of the moon forever. The moon was once much closer and much larger in our sky. When it first formed, the moon may have been only about 22,500 kilometers from Earth, compared to the roughly 384,000 kilometers that separate us today. At that distance, the moon would have appeared enormous, dominating the sky. Perhaps 20 times larger than it looks now. The tides it raised would have been catastrophic, towering walls of water sweeping across the young Earth. Over billions of years, tidal forces transferred energy from Earth's rotation to the moon's orbit, pushing it gradually outward while slowing our planet's spin. The moon we see tonight is a distant echo of what it once was, a gentle presence that was once a looming giant in the prehistoric sky. The temperature difference between lunar day and night is one of the most extreme in the solar system. With no atmosphere to distribute heat, the surface can swing from blistering hot to deathly cold within hours. At the equator during lunar noon, temperatures reach about 127 degrees Celsius. As soon as the sun sets, the temperature begins to plummet. By the middle of the lunar night, it can drop to minus 173 degrees Celsius. This is a swing of 300 degrees Celsius, enough to freeze or boil almost anything we're familiar with. Any future lunar habitats will need sophisticated thermal management systems, ways to store the day's heat for the long, cold night, or burrow deep enough underground that the temperature remains stable. The moon has been mapped in extraordinary detail. Thanks to missions like NASA's Lunar Reconnaissance Orbiter, we now have photographs of nearly every square meter of the lunar surface. We can see the Apollo landing sites, the tracks left by rovers, even individual boulders casting shadows in the morning light. This level of detail was unimaginable just a few decades ago. The maps reveal a world of stunning variety, smooth plains and rugged highlands, young craters with bright ray systems, and ancient basins softened by billions of years of bombardment. The moon is no longer a mystery hanging in the sky. It is a place, mapped and measured, and waiting to be explored once more. The moon's surface is older than almost any surface on Earth. Because of plate tectonics, erosion, and volcanic activity, Earth's surface is constantly being renewed. The oldest rocks on our planet are only about 4 billion years old, and most of the surface is far younger. The moon, by contrast, has no such processes. Its surface has remained largely unchanged for billions of years. The highlands of the moon date back to its formation 4.5 billion years ago. Some of the Maria are younger, perhaps 3 to 4 billion years old, but even these are ancient by Earth standards. When you look at the moon, you are looking at a world frozen in time, a relic of the solar system's earliest days preserved in stone and shadow. The word lunatic comes from the Latin word for moon. For centuries, people believed that the full moon could cause madness, that its silver light somehow affected the human mind in mysterious ways. Hospitals reported more admissions during full moons. Legends spoke of werewolves and strange behavior under the lunar glow. Modern studies have found no scientific evidence for these beliefs, but the language remains. We still speak of lunacy, still associate the moon with mystery and madness and things that happen in the night. The moon has always been more than a rock in the sky. It has been a symbol, a mirror, a source of wonder and fear. Even now, when we know so much about its craters and composition, it still stirs something ancient within us. And so we pause here for a moment, drifting gently through the first wonders of the moon. Already you've traveled through time, from the fiery collision that gave birth to our companion, to the frozen craters where water hides in eternal shadow. You've walked in the footprints of astronauts, felt the strange lightness of lunar gravity, and stood on mountains that have never known rain or wind, or the touch of any living thing. The moon is patient. It will wait for us to return whenever you're ready for more. But for now, if your eyes are growing heavy and your thoughts are beginning to soften around the edges, let them. There is no hurry. The facts will be here tomorrow and the night after, and for as long as the moon continues its slow, faithful orbit around our world. It has watched over countless sleepers before you, and it will watch over countless more. The moon has no sound. This might seem obvious, but it's worth sitting with for a moment. On Earth, we are surrounded by noise, the hum of appliances, the rustle of wind, the distant murmur of traffic or conversation. Even in the quietest places, there is always a something. But on the moon, there is nothing. Sound requires air to travel, and the moon has none. If a boulder tumbled down a crater wall, you would see it fall, watch the dust rise in slow motion, but you would hear absolutely nothing. The silence is total, complete, and eternal. It is a quiet beyond anything we can truly imagine, a stillness so deep it becomes almost sacred. The Apollo astronauts left mirrors on the moon that scientists still use today. These are not ordinary mirrors, but arrays of special reflectors called retroreflectors. They are designed to bounce light directly back to its source, no matter what angle it arrives from. Scientists on Earth aim powerful lasers at these mirrors and measure how long it takes for the light to return. This allows them to calculate the distance to the moon with extraordinary precision, down to the millimeter. Over the decades, these measurements have revealed that the moon is slowly drifting away from Earth and that its orbit wobbles in subtle, complex ways. The mirrors are still there, still working, still reflecting laser light back across the void, silent witnesses to one of humanity's greatest adventures. The moon's gravity is not uniform across its surface because of the maskins, those hidden concentrations of dense material beneath the Maria. The gravitational pull varies from place to place. In some regions, spacecraft experience a slightly stronger tug. In others, the pull is weaker. These variations can affect the orbits of satellites, causing them to drift over time if not corrected. Early lunar missions discovered this the hard way when their carefully planned trajectories began to shift unexpectedly. Today, we have detailed gravity maps of the moon created by spacecraft that measured these variations with exquisite precision. The moon's gravity tells a story of its interior, a hidden landscape of dense and less dense regions, shaped by ancient impacts and volcanic floods. The youngest large crater on the moon is Tycho, and it's about 108 million years old. By lunar standards, this is practically yesterday. Tycho is one of the most striking features on the moon, a bright splash of white surrounded by dramatic rays that stretch for hundreds of kilometers across the surface. These rays are made of material ejected during the impact, bright because it hasn't had as much time to be darkened by space weathering. When Tycho formed, dinosaurs still roam the Earth. The impact that created it would have been visible from our planet, a flash of light on the lunar face, a silent explosion watched by creatures who could never understand what they were seeing. The moon has helium-3 embedded in its soil, a rare isotope that could one day fuel nuclear fusion reactors. On Earth, helium-3 is extremely scarce, but the moon has been bathed in solar wind for billions of years, and particles of helium-3 have been implanted into the regolith grain by grain. Some estimates suggest there could be millions of tons of it scattered across the lunar surface. If humanity ever develops practical fusion power, the moon could become an invaluable source of fuel. Mining helium-3 would be challenging, requiring vast amounts of regolith to be processed, but it represents one of many reasons why the moon may become economically important. In the centuries to come, the moon's phases are caused by its position relative to the sun and Earth. This may seem simple, but it's worth understanding clearly. The moon doesn't produce its own light. It shines only because it reflects sunlight. As it orbits Earth, we see different portions of its illuminated half. When the moon is between us and the sun, we see only its dark side. And this is the new moon. When Earth is between the moon and the sun, we see the fully lit face, the full moon. The waxing and waning crescents and quarters are simply the stages in between, the slow reveal and concealment of the sunlit half as the moon makes its endless circuit around our world. The same side of the moon always faces Earth because of tidal locking. Long ago, the moon rotated faster, spinning freely as it orbited, but Earth's gravity created tidal bulges on the moon, slight distortions in its shape. Over millions of years, these bulges acted like brakes, slowing the moon's rotation until it matched its orbital period exactly. Now the moon rotates once for every orbit, keeping the same hemisphere eternally facing us. This is not a coincidence. It is the inevitable result of tidal forces acting over vast stretches of time. Many moons in the solar system are tidally locked to their planets. It is a common fate for close companions in gravitational embrace. The moon is slowly stealing energy from Earth's rotation. This is the mechanism behind tidal locking, and it continues even now. As the moon raises tides on Earth, friction between the moving water and the ocean floor dissipates energy. This energy comes from Earth's rotation, which means our planet is gradually spinning more slowly. Days are getting longer, by about 1.4 milliseconds per century. It's an imperceptible change on human timescales, but over hundreds of millions of years, it adds up. The dinosaurs experienced shorter days than we do. Far in the future, days could be significantly longer still. The moon is patient. It takes what it needs, one tide at a time. Lunar soil contains tiny glass beads created by ancient impacts. When meteorites strike the moon, the energy of the impact melts rock and flings it into the vacuum. Without air resistance, these molten droplets travel far before cooling, solidifying into perfect spheres of glass. They are scattered throughout the regolith, mixed with the jagged fragments and fine powder. Some are microscopic, visible only under a magnifying lens. Others are large enough to pick up between your fingers. These glass beads are time capsules, preserving information about the impacts that created them. Scientists study their composition to learn about the history of bombardment, the ages of craters, and the violence that shaped the lunar surface. The moon's interior is layered like Earth's, but much colder and more solid. At the center is a small iron core, perhaps partially molten, surrounded by a thick mantle of silicate rock. Above that lies the crust, thicker on the far side than the near side, for reasons we still don't fully understand. Unlike Earth, the moon has no active plate tectonics. Its interior has cooled to the point where large-scale geological activity has ceased. There are no volcanoes, no earthquakes from shifting plates, no mountains being pushed up by colliding continents. The moon's layers are frozen in place, relics of a more dynamic past that ended billions of years ago. The first photograph of the moon was taken in 1840 by John William Draper. It was a daguerreotype, an early photographic process that required long exposure times and produced images on polished silver plates. The photograph was grainy and indistinct by modern standards, but it captured something remarkable, proof that the tools of science could reach beyond Earth and record the face of another world. In the nearly 2 centuries since, we have photographed the moon in every wavelength of light, from every angle, with resolution fine enough to see individual boulders. But that first blurry image remains a milestone, the moment when the moon stopped being merely a light in the sky and became a place that could be studied, measured, and known. the moon experiences a phenomenon called libration, which allows us to see slightly more than half its surface over time. Although the moon is tidally locked, its orbit is not perfectly circular, and its axis is slightly tilted. This causes it to appear to wobble gently, nodding and rocking as it orbits. Because of libration, we can see about 59% of the lunar surface from Earth, not just 50%. The extra glimpses are subtle, just slivers of terrain peeking around the edges. But they add up over the course of a month. The moon, it turns out, shows us a little more than it seems, revealing hidden edges if we watch patiently enough. The moon has been visited by spacecraft from multiple countries. The United States and the Soviet Union led the way during the space race, but they are no longer alone. China has landed rovers on the lunar surface and even returned samples from the far side. India and Japan have sent orbiters to study the moon from above. The European Space Agency and private companies are planning their own missions. The moon is becoming a destination again, a place where nations and organizations compete and cooperate to explore, to learn, and perhaps one day to stay. What was once the exclusive domain of superpowers is now opening to the world. The lunar highlands are lighter in color because they are made of different rock than the Maria. The highlands are composed primarily of anorthosite, a rock rich in the mineral plagioclase, which is pale and reflete. The Maria, by contrast, are made of basalt, a darker volcanic rock that formed when lava flooded ancient impact basins. This difference in composition creates the familiar pattern of light and dark that gives the moon its face. The highlands are older, dating back to the moon's original crust. The Maria are younger, the product of volcanic activity that ended billions of years ago. Together, they tell the story of the moon's evolution, written in shades of gray. Astronauts on the moon could see Earth hanging in the sky, but it never moved. Because the moon is tidally locked, Earth always appears in roughly the same position in the lunar sky, depending on where you stand. Near the center of the near side, Earth hangs almost directly overhead, a blue and white marble suspended in the blackness. Near the edges, it hovers closer to the horizon. On the far side, it is never visible at all. For the Apollo astronauts, Earth was a constant presence, a reminder of a home that never set, never rose, just hung there in the void, slowly rotating, showing its continents and clouds, impossibly far away and yet always in sight. The moon has no weather, but it does have a kind of dust cycle. Without wind or rain, you might think nothing moves on the lunar surface, but the moon is electrically charged by the solar wind, and this charge can cause dust particles to levitate. Near the terminator, the boundary between day and night, the electric fields are strongest, and fine dust may rise and drift across the surface. Some scientists believe this electrostatic levitation is responsible for the faint glow observed on the lunar horizon during sunrise and sunset. It is not weather in any earthly sense, but it is motion, change, a subtle stirring in what seems like a frozen world. The moon's escape velocity is about 2.38 kilometers per second. This is the speed an object would need to reach to break free of the moon's gravity and fly off into space. On Earth, escape velocity is much higher, about 11.2 kilometers per second. The moon's lower gravity makes it an attractive place to launch spacecraft for deeper space missions. Less fuel is needed to escape, which means more payload can be carried. Some visionaries imagine the moon as a stepping stone, a place where spacecraft could be assembled, fueled, and launched toward Mars, the asteroids, or beyond. The moon's gentle gravity could make it a gateway to the rest of the solar system. The lunar Maria are concentrated on the near side, and no one is entirely sure why. The far side of the moon has almost no Maria at all, just endless highlands and craters. Several theories have been proposed. The near side crust may be thinner, making it easier for lava to reach the surface. The far side may have cooled faster, locking in heat before volcanism could occur. Some scientists believe the asymmetry is related to the giant impact that formed the moon, or to the way the moon's interior convected in its early days. Whatever the cause, this lopsided distribution is one of the moon's most enduring mysteries, a puzzle written across its face in light and shadow. The moon's surface is constantly being bombarded by micrometeorites. These are tiny particles, some no larger than grains of sand, that strike the surface at tremendous speeds. Over billions of years, this constant rain of impacts has pulverized the top layer of rock into the fine powder we call regolith. It has also created a process called space weathering, which darkens and alters the surface over time. Fresh craters are bright because they expose unweathered rock beneath the surface. As the centuries pass, they fade, blending into the older, darker terrain around them. The moon is being slowly ground down, grain by grain, by the relentless percussion of the cosmos. The moon has inspired countless works of art, music, and literature, from Beethoven's Moonlight Sonata to the poems of Levi, from the paintings of Van Gogh to the science fiction of Jules Verne. The moon has been a muse for as long as humans have created. It represents romance, mystery, madness, and longing. It is the destination of dreamers and the companion of the lonely. Every culture has woven the moon into its stories, its songs, its symbols. And even now, when we know so much about its craters and composition, it still stirs something within us. The moon is not just a rock in the sky. It is a mirror for the human soul, reflecting back our hopes and fears and endless wonder. The moon has a very weak magnetic field that exists only in patches. Unlike Earth, which has a global magnetic field generated by its molten core, the moon's magnetism is local and ancient. Certain regions of the crust retain magnetic signatures from a time when the moon may have had an active core. These magnetic anomalies are puzzling because they don't form any obvious pattern. Some may be associated with ancient impact basins or volcanic features. Others seem random. They are remnants of a younger moon, a moon that was still warm and dynamic before its heart cooled and its field faded into silence. The Apollo missions brought back 382 kilograms of lunar samples. These rocks and the soil samples have been studied by scientists around the world for more than 50 years. They have revealed the moon's age, its composition, its volcanic history, and the conditions of the early solar system. Many samples are still sealed in pristine containers, waiting for future technologies that can extract even more information. The lunar samples are among the most valuable scientific specimens on Earth. Pieces of another world, brought home by 12 brave humans who walked where no one had walked before. They are treasures beyond price, windows into the deep past of our cosmic neighborhood. The lunar roving vehicle allowed astronauts to travel several kilometers from their landing site. On the later Apollo missions, astronauts drove these electric vehicles across the lunar surface, exploring craters, collecting samples, and covering distances that would have been impossible on foot. The rovers were simple by modern standards, little more than frames with wheels and seats, but they transformed what was possible during a moonwalk. They are still there, parked on the surface, their batteries long dead, their tires slowly degrading in the harsh radiation. Monuments to human ingenuity, waiting in the silence for someone to visit them again. The moon's orbit is tilted about 5 degrees relative to Earth's orbit around the sun. This is why we don't have a solar eclipse every new moon or a lunar eclipse every full moon. Usually, the moon passes above or below the line between Earth and the sun, missing the alignment needed for an eclipse. Only when the moon crosses the plane of Earth's orbit at the right moment do we see these spectacular events. The tilt is subtle, but it shapes the rhythm of eclipses, creating patterns that ancient astronomers learned to predict and that still inspire wonder today. The moon may have had a brief atmosphere billions of years ago. During its volcanic period, when lava was flooding the Maria, gases would have been released from the interior. For a few tens of millions of years, the moon may have been wrapped in a thin veil of carbon monoxide, sulfur, and other volcanic gases. It wasn't much of an atmosphere, certainly nothing like Earth's, and it would have been lost to space relatively quickly. But for a moment in deep time, the moon breathed. It exhaled the remnants of its inner fire before falling silent, before becoming the airless world we know today. The regolith on the moon can be several meters deep in some places. In the Maria, where micrometeorite bombardment has been working on relatively soft basalt for billions of years, the soil can be quite thick. In the highlands, where the rock is harder and older, the regolith is often thinner. This dusty layer is not just debris. It is a record of time, a stratified archive of impacts, solar wind implantation, and cosmic ray exposure. Scientists who study regolith samples can read this record, extracting information about events that happened billions of years ago. The dust remembers what the moon has experienced. The moon's gravity helps stabilize Earth's axial tilt. Our planet spins at an angle of about 23.5 degrees relative to its orbit, and this tilt gives us our seasons. Without the moon's gravitational influence, Earth's tilt could wobble chaotically over millions of years, swinging from nearly upright to lying almost on its side. Such extreme variations would cause dramatic climate shifts, making it harder for life to adapt and survive. The moon acts as a stabilizer, a gravitational anchor that keeps our tilt within a narrow range. We owe our relatively stable climate, at least in part, to the steady presence of our lunar companion. Some craters on the moon are named after deceased astronauts and cosmonauts. In addition to the great scientists and explorers of the past, the International Astronomical Union has honored those who gave their lives in the pursuit of space exploration. The crews of Apollo 1, Challenger, and Columbia are remembered in lunar nomenclature, as are Soviet cosmonauts who died in the line of duty. These names transform the map of the moon into a memorial, a quiet tribute to those who risked everything to push the boundaries of human knowledge. Their names will endure for as long as the craters themselves etched into the ancient stone of another world. The moon's crust is thicker on the far side than the near side. On the near side, facing Earth, the crust averages about 60 kilometers thick. On the far side, it can be nearly twice that. This asymmetry helps explain why the Maria are concentrated on the near side. When large impacts occurred, magma had an easier time reaching the surface through the thinner, near-side crust. On the far side, the thick crust acted as a barrier, preventing lava from flooding the basins. The origin of this crustal difference is still debated. Some scientists believe it relates to the way the moon solidified after its formation. Others think it may be connected to tidal forces from the early Earth. Whatever the cause, it has shaped the moon's appearance in profound ways. The moon has been used to test Einstein's theory of general relativity. By bouncing laser beams off the retroreflectors left by Apollo astronauts, scientists can measure the moon's distance with incredible precision. These measurements have confirmed predictions made by Einstein's theory, including subtle effects of gravity on the passage of time and the curvature of space. The moon has become a laboratory for fundamental physics, a proving ground for our deepest theories about the nature of the universe. What began as a destination for exploration has become a tool for understanding reality itself. The Shackleton crater at the lunar South Pole is one of the most intriguing locations for future exploration. Its floor lies in permanent shadow, never seeing sunlight, making it one of the coldest places in the solar system. Water ice almost certainly exists there, preserved for billions of years. But the crater's rim receives almost constant sunlight, offering a source of solar power. This combination of resources makes Shackleton a prime candidate for a future lunar base. Astronauts could live on the rim, harvest ice from the depths, and operate in conditions more hospitable than almost anywhere else on the moon. It is a place where science fiction could become reality. The moon's orbit is gradually becoming more circular over time. When the moon first formed, its orbit was likely more elliptical than it is today. Tidal forces between Earth and the moon have been working for billions of years to smooth out this path, transferring energy and angular momentum in subtle ways. The process is slow, almost imperceptibly so, but it continues even now. In the distant future, the moon's orbit will be even more circular than it is today, and Earth's rotation will have slowed further. The dance between our two worlds is still evolving, still adjusting, still finding its balance. The moon has inspired the development of new technologies. The challenge of sending humans to the moon and returning them safely pushed engineers to invent materials, computing systems, and life support technologies that had never existed before. Many of these innovations found their way into everyday life. Memory foam, freeze-dried food, water purification systems, and advances in computer miniaturization all trace their lineage to the Apollo program. The moon was not just a destination, it was a catalyst, a challenge that forced humanity to stretch its capabilities and dream of what might be possible. The lunar surface is electrically charged by the solar wind. Streams of charged particles from the sun constantly bombard the moon, depositing electrons and ions on the surface. On the day side, ultraviolet light knocks electrons loose, giving the surface a positive charge. On the night side, electrons accumulate, creating a negative charge. This creates complex electric fields, especially near the terminator, the boundary between light and shadow. These fields can levitate dust particles and may pose challenges for future equipment and habitats. The moon is not just a dead rock, it is an electrically active environment shaped by invisible forces from the sun. The first soft landing on the moon was achieved by the Soviet Luna 9 spacecraft in 1966. Before this, no one knew for certain whether a spacecraft could land on the lunar surface without sinking into deep dust. Some scientists feared the regolith might be so fine and deep that anything landing would simply disappear into it. Luna 9 proved otherwise, touching down safely and transmitting the first photographs from the surface. These grainy images showed a rocky, solid landscape and dispelling fears and paving the way for human landings just 3 years later. It was a triumph of engineering and courage, a moment when uncertainty gave way to knowledge. The moon's Maria have fewer craters than the highlands because they are younger. When lava flooded the ancient impact basins, it buried the craters that had existed before, creating smooth plains. Since then, the Maria have accumulated new craters from ongoing impacts, but they haven't had as much time to collect them as the ancient highlands. By counting craters, scientists can estimate the age of different surfaces. More craters mean older terrain. Fewer craters mean younger. The moon's face is a clock, its wrinkles and scars marking the passage of billions of years. The full moon is about 9 times brighter than a half moon. This might seem surprising since a half moon shows half the illuminated surface, but the full moon benefits from a phenomenon called the opposition surge. When the sun is directly behind the observer, shadows on the lunar surface disappear, and the surface reflects light more efficiently. The result is a dramatic increase in brightness. This is why a full moon can seem so brilliant, almost dazzling, while a quarter moon is pleasantly dim. The geometry of light and shadow makes all the difference. The moon has a trail of debris in its orbit called the Kordylewski clouds. These are faint concentrations of dust that gather at gravitationally stable points in the Earth-Moon system, known as Lagrange points. They were predicted decades ago, but only confirmed recently through careful observation. The clouds are extremely diffuse, barely visible even with sensitive instruments. But they are there, ghostly companions to the moon, drifting along its orbital path like shadows. They are a reminder that even empty space is not truly empty, that gravity shapes subtle structures we are only beginning to see. The moon's South Pole Aitken Basin is one of the oldest and largest impact structures in the solar system. It stretches about 2,500 kilometers across and plunges more than 8 kilometers deep. The impact that created it would have been cataclysmic, occurring early in the moon's history when the solar system was still full of debris. The basin may have excavated material from the moon's mantle, offering scientists a window into the lunar interior. Missions to study this ancient scar could reveal secrets about the moon's formation and the violent early days of our cosmic neighborhood. The moon appears to change color near the horizon. When it's low in the sky, moonlight must pass through more of Earth's atmosphere to reach your eyes. This scatters blue light away and allows red and orange wavelengths to dominate. The result is a moon that can appear golden, orange, or even deep red as it rises or sets. The effect is strongest when the atmosphere contains dust or smoke, which scatters light even more. A harvest moon glowing amber over autumn fields is not a trick of the imagination. It is physics made beautiful, the atmosphere painting the moon in warm colors as it climbs above the horizon. The lunar day and night create extreme engineering challenges for solar-powered equipment. During the 2-week lunar night, solar panels produce no power at all. Batteries must sustain all operations, or equipment must enter hibernation mode. The cold is so intense that electronics can crack and fail. During the lunar day, the challenge reverses. Equipment must shed heat efficiently or risk overheating. These extremes have limited the duration of many lunar missions. Future long-term bases will need nuclear power or massive battery systems to survive the relentless cycle of light and darkness that defines life on the moon. The moon has inspired religious and spiritual traditions around the world. In many cultures, the moon is associated with deities, most often female goddesses of fertility, change, and the night. Selene in Greek mythology, Luna in Roman tradition, Chang'ai in Chinese legend. The cycles of the moon have been used to mark holy days, festivals, and rituals for thousands of years. The Islamic calendar is lunar, as is the Jewish calendar for determining religious observances. Even today, the moon holds spiritual significance for millions of people, a celestial body that connects humanity to the rhythms of the cosmos and the mysteries of existence. The terminator is the name for the line that separates day from night on the moon. It is not a sharp edge, but a gradual transition where long shadows stretch across craters and mountains stand out in dramatic relief. Astronomers consider the terminator one of the best places to observe lunar features through a telescope because the low angle of sunlight reveals textures and depths that are invisible when the sun is overhead. As the moon orbits Earth, the terminator sweeps slowly across the surface, illuminating new features and plunging others into darkness. It is a moving boundary between light and shadow, a slow tide of visibility washing across the ancient stone. And so we pause once more, having wandered through another chapter of lunar wonders. You've heard the moon's silence, seen the laser light bouncing off mirrors left by astronauts, and learned of the slow theft of energy that lengthens our days. You've touched glass beads forged in ancient impacts and glimpsed the faint shimmer of levitating dust on the horizon. The moon continues its patient orbit, as it has for billions of years, as it will for billions more. It asks nothing of you tonight. It offers only its light, its stillness, and its ancient stories. If your eyes are heavy and your mind is drifting, let them. Sleep is a gift, and the moon will watch over you as you receive it, so let yourself settle again. Let the weight of the day fall away. Let your thoughts grow soft and slow, and let the moonlight guide you a little deeper into the night. There is no rush. The moon has been here for billions of years. It will wait as long as you need. Now let's continue. The moon has swirls. Scattered across the lunar surface are mysterious, bright patterns called lunar swirls. They look almost like someone painted them on, curving and looping across the dark Maria in pale brushstrokes. Scientists are not entirely sure what causes them. Some believe they are related to localized magnetic fields that deflect the solar wind, preventing the surface from darkening as quickly. Others think they may be connected to ancient comet impacts. The swirls do not correspond to any obvious topography. They lie flat across the terrain, ignoring craters and hills. They are beautiful, unexplained, and waiting for someone to uncover their secret. The moon is thought to have formed within just a few hours of the giant impact. When the Mars-sized body struck the young Earth, the debris disk that formed was hot, turbulent, and fast-moving. Computer simulations suggest that the material coalesced into the moon remarkably quickly, perhaps in as little as a few hours to a few days. This rapid formation would have left the new moon molten, glowing like a second sun in Earth's sky. Over millions of years, it cooled, solidified, and became the quiet companion we know today. But for a brief, violent moment, the moon was born in fire and chaos, faster than anyone might have imagined. The moon's cratered surface was once thought to be volcanic in origin. Before the space age, many scientists believed that lunar craters were the remnants of ancient volcanoes. The round shapes and raised rims seemed consistent with volcanic calderas. It wasn't until spacecraft visited the moon and returned samples that the impact origin became clear. The craters were not vents, but scars, the marks of countless collisions over billions of years. This realization changed our understanding, not just of the moon, but of the entire solar system. Impact cratering, once thought to be rare, was revealed as a fundamental process that shaped every rocky world. The moon's far side was first seen by human eyes in 1968 during the Apollo 8 mission. Frank Borman, Jim Lovell, and William Anders became the first people to travel behind the moon and lose contact with Earth. For about 45 minutes on each orbit, they were completely alone, cut off from all of humanity by 300-400 kilometers of ancient rock. What they saw was a landscape unlike the near side. No familiar Maria, just an endless expanse of craters, battered and gray. They also witnessed something else. As they emerged from behind the moon, they saw Earth rising over the lunar horizon. That image, captured by Anders, became one of the most famous photographs in history, a reminder of our small, fragile home. The moon experiences temperature swings of over 300 degrees Celsius. In the vacuum of space, without an atmosphere to moderate the extremes, the lunar surface bakes in sunlight and freezes in shadow. Noon at the equator can reach a 127 degrees Celsius. Midnight can plunge to minus 173 degrees. Even within a single crater, the sunny rim might be scorching, while the shadowed floor is colder than anywhere on Earth. These extremes are one of the greatest challenges for lunar exploration. Materials expand and contract. Electronics fail. Human bodies cannot survive without protection. The moon is beautiful, but it is not hospitable. It demands respect. The first living creatures to travel around the moon were tortoises. In 1968, the Soviet Sonda 5 spacecraft carried 2 Russian steppe tortoises, along with other biological samples, on a loop around the moon and back to Earth. The tortoises survived the journey, experiencing weightlessness and cosmic radiation, before splashing down in the Indian Ocean. They lost a little weight, but were otherwise healthy. This mission demonstrated that living organisms could survive the journey to the moon and back, paving the way for human missions. The tortoises never knew the significance of their voyage, but they became pioneers nonetheless. The first Earth creatures to see the far side of the moon passed beneath them. The moon has no permanent human presence, but plans are underway to change that. Multiple space agencies and private companies are developing programs to return humans to the lunar surface and eventually establish permanent bases. NASA's Artemis program aims to land astronauts near the South Pole, where water ice could support long-term habitation. China has announced plans for a lunar research station. Private companies are designing landers, habitats, and rovers. The moon, dormant as a destination for over 50 years, is once again becoming a focus of human ambition. The next footprints may come within this decade, and they may be followed by many more. The moon's orbit is slowly expanding at a known rate because of tidal friction. As the tides slosh back and forth in Earth's oceans, friction converts some of Earth's rotational energy into heat. This energy is transferred to the moon, pushing it into a higher orbit. The rate of expansion, about 3.8 centimeters per year, has been measured precisely using the laser reflectors left by Apollo astronauts. Over the course of a human lifetime, the moon moves only about 3 meters farther away. But over geological time, the effect is profound. The moon was once much closer, and in the distant future, it will be much farther. Nothing in the cosmos stays the same forever. The moon has been struck by spacecraft intentionally to study what lies beneath its surface. In 2009, NASA's L-Cross mission deliberately crashed a rocket stage into a permanently shadowed crater near the South Pole. The impact sent a plume of debris into the sunlight, where instruments could analyze its composition. The results confirmed the presence of water ice, along with other volatile compounds. This technique, called impact spectroscopy, allows scientists to study materials that would otherwise be impossible to reach. The moon bears the scars of these deliberate impacts now. Small marks left by our quest to understand what secrets it holds. The moon's gravity causes the length of Earth's day to increase by about 2.3 milliseconds per century. This is the same tidal friction that pushes the moon away. As the moon steals energy from Earth's rotation, our planet spins a little more slowly. The effect is tiny on human timescales, but it accumulates. Ancient coral fossils show that hundreds of millions of years ago, there were more days in a year because each day was shorter. In the distant past, a day might have been only 22 hours long. In the distant future, days could stretch much longer. The moon is patient, taking what it needs one tide at a time, slowing us down so gently we never notice. The lunar regolith contains tiny particles of pure iron. Unlike the iron found on Earth, which is usually combined with other elements in ores, this iron exists as microscopic metallic grains scattered throughout the soil. It forms through a process called space weathering, where micrometeorite impacts and solar wind bombardment reduce iron-bearing minerals to their pure metal form. These tiny iron particles contribute to the moon's unusual optical properties and help scientists understand how airless bodies change over time. The iron has been there for billions of years, waiting in the dust, pure and patient, a gift from the relentless rain of the cosmos. The moon has been proposed as a site for astronomical observatories. Without an atmosphere to blur the stars or scatter light, the lunar surface offers pristine viewing conditions. A radio telescope on the far side would be shielded from Earth's electromagnetic noise, able to detect faint signals from the early universe. Optical telescopes could observe without the twinkling that plagues ground-based instruments. The long lunar night would allow extended observations without interruption from sunlight. Building such observatories would be enormously challenging, but the scientific rewards could be profound. The moon might one day become humanity's greatest window onto the cosmos. The concept of a blue moon has nothing to do with color. In common usage, a blue moon is the second full moon in a calendar month, a relatively rare occurrence that happens about once every 2 or 3 years. The phrase gave rise to the expression, once in a blue moon, meaning something that happens infrequently. In reality, the moon can appear blue in exceptional circumstances, such as when volcanic ash or forest fire smoke fills the atmosphere with particles of just the right size to scatter red light. But these truly blue moons are far rarer than the calendrical kind. Most blue moons are simply full moons that happen to fall at an unusual time. The moon's surface has been walked on by geologists. Harrison Schmitt, who flew on Apollo 17, was a trained geologist, the only professional scientist to walk on the moon. His expertise allowed him to recognize and collect samples that might have been overlooked by astronauts without geological training. He identified orange soil near Shorty Crater, which turned out to be tiny glass beads created by ancient volcanic eruptions. His presence on the mission demonstrated the value of sending scientists, not just pilots, to explore other worlds. Future lunar missions will likely include specialists from many fields, each bringing unique skills to the ancient surface. The moon has a thin tail of sodium atoms that streams away from it like a comet. Solar radiation and micrometeorite impacts knock sodium atoms loose from the surface, and the pressure of sunlight pushes them into a faint tail that extends for thousands of kilometers. This sodium tail is invisible to the naked eye, but it can be detected with sensitive instruments. It's a reminder that the moon is not a static object, but an active participant in the space environment, constantly interacting with sunlight, solar wind, and the stream of particles that fills the solar system. Even the moon has a kind of breath, a faint exhalation of atoms drifting into the void. The Apollo 11 landing site is now considered a heritage site by some organizations, although no international law protects it. There have been proposals to designate the Tranquility Base area as a protected location, preserving the footprints, equipment, and flag left behind by Neil Armstrong and Buzz Aldrin. As more nations and private companies plan lunar missions, the question of how to protect these historic sites becomes more pressing. The first human footprints on another world represent one of humanity's greatest achievements. Many believe they deserve protection, not just as scientific artifacts, but as monuments to courage and curiosity that belong to all of humanity. The moon has been mapped in 3 dimensions using laser altimetry. Spacecraft like NASA's Lunar Reconnaissance Orbiter have bounced billions of laser pulses off the surface, measuring the distance with extreme precision. The result is a detailed topographic map showing every crater, mountain, and valley. We know the heights of lunar peaks and the depths of its basins with accuracy measured in meters. This data is essential for planning future landing sites and understanding the moon's geological history. The moon, once a mysterious light in the sky, is now one of the most thoroughly mapped bodies in the solar system. The lunar Maria were formed between 3.1 and 3.8 billion years ago. This period, known as the Late Heavy Bombardment, saw the inner solar system swept by asteroids and comets. Large impacts created the basins that would later fill with lava. As the bombardment tapered off, volcanic activity flooded these basins, creating the smooth, dark plains we see today. The Maria are younger than the highlands, but still ancient by any earthly standard. They have witnessed the entire history of life on Earth, from the first single-celled organisms to the astronauts who walked across their surface. They are quiet witnesses to time beyond comprehension. The moon has been used as a gravitational slingshot to send spacecraft to other destinations. By flying close to the moon and using its gravity to change direction and speed, spacecraft can save fuel and reach places that would otherwise be inaccessible. This technique has been used to send probes to asteroids, to the sun, and to distant orbits around Earth. The moon's gravity, which once pulled our ancestors' tides and inspired their myths, has become a practical tool for exploration. It bends trajectories and boosts velocities, a silent partner in humanity's reach toward the stars. The moon's regolith could be used to make building materials. Lunar soil contains silicates and metals that, with the right processing, could be sintered or melted into bricks, panels, and other structural components. This technique, called in situ resource utilization, would dramatically reduce the cost and complexity of building on the moon. Instead of launching everything from Earth, future settlers could manufacture what they need from local materials. The regolith that once seemed like a nuisance, clogging equipment and scratching visors, could become the foundation of a new human presence on another world. The moon influences animal behavior on Earth. Many species time their activities to the lunar cycle. Coral spawn in synchrony with full moons. Some birds navigate by moonlight during migration. Certain predators hunt more successfully under the bright full moon, while their prey hides in the shadows. Even human sleep patterns show subtle correlations with the lunar cycle, though the effects are small and debated. The moon's influence on life extends far beyond the tides. It is woven into the rhythms of the natural world, a celestial clock that creatures have followed for millions of years without ever knowing its name. The moon reminds us that we are not alone in the universe, even if we are the only ones looking back. It is the only other world humans have ever touched. It carries our footprints, our flags, our mirrors, and our machines. It has washed over every generation of humans who ever lived, from the first who gazed up in wonder to the scientists who study it with lasers and spacecraft. The moon does not judge. It does not demand. It simply orbits, quiet and patient, reflecting the sun's light into our night sky. It is a companion, a mystery, and a destination. And tonight, as you drift towards sleep, it is watching over you, just as it always has. But perhaps there are a few more quiet thoughts to share before we rest. The moon, after all, is inexhaustible. Every crater has a story. Every grain of dust holds memory. And so let us linger a little longer in its gentle light. The moon has no global ocean, but it may have had small pockets of liquid water in the past. Some scientists believe that during volcanic eruptions billions of years ago, water vapor was released along with other gases. For brief periods, the moon may have had a thin atmosphere capable of supporting liquid water on the surface. These conditions would have been temporary, lasting perhaps only a few million years before the water escaped into space or froze in the shadows. The idea of ancient lunar water is still debated, but it speaks to a time when the moon was more dynamic, more alive, more like the world we call home. The moon's light has guided sailors across oceans for thousands of years. Before GPS, before lighthouses, Before even the magnetic compass was widely used, the moon was a beacon for travelers. Its phases helped mark the passage of time. Its position in the sky indicated direction. Fishermen knew that certain fish were more active under the full moon. Farmers planted crops according to lunar calendars. The moon was not just a pretty light. It was a tool, a guide, a partner in the business of survival. Even now, when we have satellites and smartphones, the moon remains a symbol of guidance, a light in the darkness that has always been there. The moon's far side is sometimes called the quiet side because it is shielded from Earth's radio noise. Our planet is a cacophony of signals, broadcasts, and electromagnetic chatter that spills out into space. But the far side of the moon, always facing away from Earth, is protected from this noise. Radio telescopes placed there could listen for faint signals from the distant universe without interference. They might detect emissions from the cosmic dark ages, the era before the first stars formed, when the universe was filled only with hydrogen. The far side is not dark in terms of light, but it is quiet in terms of radio, a place of profound cosmic silence. The moon has been a testing ground for theories of planetary formation. By studying lunar rocks, scientists have learned not just about the moon, but about how all rocky planets form and evolve. The processes of differentiation, where heavy elements sink to form a core, while lighter elements rise to form a crust, were first understood in detail through lunar samples. The history of impacts, volcanism, and cooling that shaped the moon provides a template for understanding worlds throughout the solar system. Mars, Mercury, asteroids, and even the early Earth all share elements of this story. The moon is a classroom, and we are still learning. The gravitational pull of the moon is so gentle that you would never feel it. On Earth, you are pulled toward the moon with a force about 3 million times weaker than Earth's own gravity. It's not enough to lift you, not enough to make you feel lighter, not even enough to notice. And yet this imperceptible force is enough to raise the oceans, to bend the shape of our planet, to slow our rotation over billions of years. The moon's influence is a reminder that small forces, acting consistently over time, can reshape worlds. Patience is power. The moon knows this better than anyone. The smell of moon dust, according to astronauts, resembles gunpowder or burnt charcoal. When lunar dust was brought inside the spacecraft and exposed to air, it produced a distinctive odor that surprised the astronauts. The cause is not fully understood, but it may be related to the highly reactive nature of freshly exposed regolith. On the moon's surface, the dust is constantly bombarded by radiation and micrometeorites, creating broken chemical bonds that react immediately when they encounter oxygen and moisture. The smell of the moon is the smell of chemistry in action, of a surface that has never known air suddenly meeting the breath of Earth. The moon appears to be the same size as the sun in our sky. But this is a temporary coincidence. The moon is slowly moving away from Earth, and millions of years in the future, it will appear smaller. Billions of years ago, it would have appeared much larger. We happen to live in the brief window of cosmic history when the angular sizes match closely enough to produce perfect total solar eclipses, where the moon's disk exactly covers the sun's photosphere, while allowing the corona to blaze around the edges. This coincidence may be unique in the known universe? If so, we are extraordinarily fortunate to witness it. The moon has been used to calibrate instruments on spacecraft studying other worlds. Because we know the moon's composition and reflectivity so well, spacecraft can point their instruments at the moon to check their accuracy before turning to more distant targets. The moon serves as a standard, a reference point, a known quantity against which unknowns can be measured. In this way, our familiar companion helps us understand worlds billions of kilometers away. The moon is not just a destination, it is a tool, a benchmark, a stepping stone to the rest of the cosmos. The first words spoken from the surface of the moon were not about the moon at all, before Neil Armstrong delivered his famous line about a small step. The first words transmitted were technical call signs and status reports. Contact light, followed by confirmations that the engine had been shut down and the spacecraft was stable. The historic moment was wrapped in the mundane language of engineering, a reminder that even the greatest achievements are built on countless small, careful steps. The poetry came later. First came the work. The moon continues to accrete material, even now. Every year, about 5,000 tons of cosmic dust settle onto the Earth-Moon system. Most of it burns up in Earth's atmosphere as meteors, but some fraction reaches the lunar surface. The moon grows imperceptibly, grain by grain, year after year. It is not the same moon that formed 4.5 billion years ago. It carries the accumulated dust of ages, the remnants of asteroids and comets from across the solar system. The moon is still being built, still being shaped, still growing in the silence of space. The longest time any human has spent on the lunar surface was about 75 hours. Eugene Cernan and Harrison Schmitt, during the Apollo 17 mission, explored the Taurus-Littrow Valley for just over 3 days. They conducted 3 moonwalks, collected samples, and drove the lunar rover across the ancient terrain. And then they left, becoming the last humans to walk the moon. That was in December of 1972. More than 50 years have passed, and the record still stands. The footprints they left are still there, undisturbed in the dust, waiting for someone to return and add their own. The moon has witnessed every sunrise and sunset in Earth's history. It has seen continents drift, oceans rise and fall, ice ages come and go. It watched the first fish crawl onto land and the last dinosaur fall. It has seen empires rise and crumble, wars begin and end, and countless ordinary moments that no one remembers. The moon does not record these events. It simply orbits, silent and unchanging, while the world below transforms again and again. And yet in some sense, it has been there for all of it, a constant presence in an ever-changing sky, a witness to everything we have been and everything we might become. The moon will outlive human civilization, no matter what happens. Even if our species vanishes, the moon will continue its orbit. The footprints will eventually be erased by micrometeorites over millions of years. The flags will disintegrate. The equipment will be buried in dust. But the moon itself will endure, orbiting a silent Earth or drifting alone if some catastrophe destroys our planet. It was here before us, and it will be here long after. This is not a sad thought. It is a reminder of scale, of time, of the vast indifference of the cosmos. The moon does not need us, but perhaps in some small way, we need it. Every astronaut who walked on the moon reported a profound shift in perspective. They called it the overview effect, though on the moon it was even more intense. Seeing Earth as a small, fragile sphere hanging in the blackness of space changed something deep within them. Political borders became invisible. The conflicts that divided nations seemed petty and small. The thin blue line of atmosphere looked impossibly delicate. Many returned with a new sense of responsibility for our planet, a conviction that humanity must learn to live together or risk losing the only home we have ever known. The moon gave them distance, and distance gave them clarity. The moon has valleys, rills, and sinuous channels carved by ancient lava flows. Some of these features stretch for hundreds of kilometers, winding across the Maria like dry riverbeds. They were formed when molten rock flowed across the surface billions of years ago, sometimes carving channels through existing terrain, sometimes leaving collapsed lava tubes behind. These tubes, if they still exist intact beneath the surface, could provide natural shelter for future explorers, protected from radiation, micrometeorites, and temperature extremes. Lava tubes might become the first homes for humans on another world. The moon has been photographed by more spacecraft than any other celestial body beyond Earth. Dozens of orbiters, landers, and rovers from multiple countries have captured images of its surface in every wavelength of light. We have photographs from the ground showing the curvature of the horizon, images from orbit revealing the full disk in stunning detail, and maps assembled from millions of individual measurements. The moon is perhaps the most documented object in the solar system, and yet new missions continue to reveal features we had never noticed before. Familiarity has not bred contempt. It has only deepened our wonder. The coldest temperatures in the solar system have been measured in permanently shadowed craters on the moon. Some of these locations are colder than the surface of Pluto, reaching temperatures below minus 240 degrees Celsius. The craters act as cold traps, accumulating ice and other volatiles that cannot escape once they settle there. These frozen reservoirs have been undisturbed for billions of years, preserving a record of materials delivered by comets and asteroids throughout the solar system's history. They are archives of the past, frozen in time, waiting for future explorers to unlock their secrets. The moon's orbit is not fixed, but wobbles in complex patterns over decades and centuries. The plane of the orbit tilts and precesses, causing the moon to appear higher or lower in the sky over cycles lasting about 18.6 years. These variations affect the severity of tides, the frequency of eclipses, and even the amount of moonlight reaching polar regions on Earth. Ancient astronomers noticed these patterns and used them to predict eclipses with remarkable accuracy. The moon's dance is not simple, but it is predictable. It follows rules written in gravity, playing out the same motions generation after generation. The moon contains rocks that formed from the primordial magma ocean. When the moon was young and still molten, its entire surface was covered in a sea of liquid rock. As this ocean cooled, minerals crystallized and separated by density. Light minerals floated to the top, forming the ancient highlands. Heavier minerals sank, contributing to the mantle. Some lunar samples preserve crystals that formed directly from this primordial ocean, rocks that have existed for 4.4 billion years, nearly as old as the moon itself. Holding one of these samples is like touching the beginning of time. The Apollo missions left behind more than just footprints and flags. They left seismometers that recorded moonquakes for years. They left laser reflectors that scientists still use today. They left cameras, tools, and personal items. Alan Shepard hit golf balls. The crews left commemorative plaques and medallions honoring fallen astronauts and cosmonauts. These objects remain on the surface, scattered across 6 landing sites, slowly aging in the vacuum and radiation. They are artifacts of a remarkable moment in human history, when we reached beyond our world and touched another. They wait there still, monuments to what we can achieve when we dare to dream. The moon will never feel the wind, hear a sound, or know the touch of rain. It exists in a state of absolute stillness that is difficult for earthbound minds to truly comprehend. Every landscape you have ever seen has been shaped by water, air, or life. The moon has none of these. Its mountains were raised by impacts, not by tectonic forces. Its valleys were carved by lava, not by rivers. Its dust was ground by meteorites, not by weather. It is a world of pure geology, uncomplicated by the messy processes that make Earth so dynamic. In its stillness, it offers a kind of peace, a reminder that not all worlds need to be alive to be beautiful. And finally, the moon is yours. It belongs to every person who has ever looked up and wondered. It belongs to the child staring out a window at night and the astronomer peering through a telescope. It belongs to poets and scientists, dreamers and skeptics, to everyone who has ever felt small beneath the stars and found comfort in that smallness. No nation can own it. No corporation can claim it. The moon is a shared inheritance, a common treasure that unites humanity across every border and generation. And tonight, as you drift toward sleep, it shines for you alone, even as it shines for everyone else, patient and eternal and full of light. And so we come to the end of our journey across the moon. 100 facts, 100 quiet wonders, 100 glimpses into the history and mystery of our nearest neighbor in space. You have traveled far tonight. You have walked in the footsteps of astronauts, felt the silence of a world without air, and touched the ancient dust that remembers the birth of the solar system. The moon will continue its orbit long after this night has ended. It will wax and wane, rise and set, pull the tides and light the darkness. It asks nothing of you. It offers only its presence, steady and calm, a reminder that there is always something larger than ourselves, something ancient and enduring that watches over the Earth. The Apollo program was one of the most ambitious undertakings in human history. Between 1969 and 1972, 12 human beings walked on the surface of another world. They traveled 250,000 miles through the vacuum of space, landed on an alien landscape, explored it with their own hands and eyes, and returned safely to Earth. The technology that made this possible was, by modern standards, almost primitive. The onboard computers had less processing power than a basic calculator. The spacecraft were held together by rivets and hope. And yet it worked. It worked because thousands of engineers solved thousands of problems, because astronauts trained until every procedure was a second nature, and because an entire nation decided that reaching the moon was worth the effort and the risk. The astronauts who made those journeys were test pilots and engineers, men chosen for their ability to remain calm under pressure. But they were also human beings, capable of wonder and awe. Neil Armstrong, the first to step onto the lunar surface, was famously reserved, a man who let his actions speak louder than words. Buzz Aldrin, who followed him minutes later, described the moon as magnificent desolation. The crews of later missions explored mountains and valleys, collected rocks that would rewrite our understanding of planetary science, and drove a car across terrain that no wheel had ever touched. And then it ended, after Apollo 17 lifted off in December 1972. No human being has returned. The flags the astronauts planted still stand, bleached white by decades of radiation. The footprints remain, preserved in the airless silence. The equipment they left behind continues to function in some cases, still reflecting laser light back to Earth. The Apollo program was a triumph and a tragedy. A triumph because it proved what humanity could achieve. A tragedy because we stopped, turned away, and let half a century pass without going back. But perhaps the story is not over. Perhaps the next chapter is just beginning. The moon is a geologist's dream and a geologist's puzzle. Its surface is a record of processes that have largely ceased, frozen in time for billions of years. Unlike Earth, where plate tectonics constantly recycle and renew the crust, the moon's surface preserves the scars of its earliest history. The highlands are made of anorthosite, a rock that crystallized from the primordial magma ocean when the moon was still young and molten. These pale, ancient terrains are among the oldest surfaces in the solar system, dating back more than 4 billion years. The Maria tell a different story. They are made of basalt, a dark volcanic rock that formed when lava flooded the Great Impact Basins. This volcanism occurred between 3 and 4 billion years ago, during a period when the moon's interior was still hot enough to generate magma. The lava flows were enormous, covering thousands of square kilometers and burying the older, cratered terrain beneath smooth, dark plains. When the volcanism ended, the Maria froze in place, and the moon began its long, slow cooling into the quiet world we see today. The craters that dot the surface are impact scars created when asteroids and comets struck at tremendous speeds. The largest impacts excavated basins hundreds of kilometers across and threw debris across the entire moon. Smaller impacts created the countless craters that overlap and to crowd every surface. By counting craters, scientists can estimate the age of different terrains. More craters mean older surfaces. The rate of impacts has declined over time, but it has never stopped entirely. Even today, small meteorites strike the moon, adding new craters to a surface already saturated with the scars of the past. The moon has been part of human culture for as long as there have been humans. Our earliest ancestors watched it rise and set, noticed its phases, and wove it into their understanding of the world. The moon became a god, a goddess, a symbol of change and constancy, of death and rebirth. Calendars were built around its cycles. Festivals were timed to its phases. The moon was a clock, a compass, and a companion, always present, always changing, always the same. In ancient Mesopotamia, the moon god Sin was one of the most important deities, worshipped in great temples and celebrated with elaborate rituals. In Greece, Selene drove her silver chariot across the night sky, while Artemis, goddess of the hunt, was associated with the crescent moon. In China, Chang'e fled to the moon and became its spirit, a accompanied by a jade rabbit who pounds the elixir of immortality. In Japan, the moon viewing festival of Tsukimi celebrates the autumn moon with offerings of rice dumplings and pampas grass. Every culture has found meaning in the moon, projecting their hopes, fears, and dreams onto its silent face. The moon has inspired poets and artists for millennia. Levi wrote of drinking alone beneath the moon, making 3 companions of himself, his shadow, and the lunar light. Beethoven's Moonlight Sonata captures something of the moon's melancholy beauty. Van Gogh painted starry nights with moons that swirl and glow. The moon appears in love songs and lullabies, in epic poems and children's rhymes. It is the destination of dreamers and stories by Jules Verne and H.G. Wells. It is the backdrop for romance and mystery, for werewolves and witches. The moon is not just an astronomical object. It is a mirror for the human imagination. After decades of dormancy, the moon is becoming a destination again. NASA's Artemis program aims to return humans to the lunar surface. This time, to stay. The goal is not just to plant flags and collect rocks, but to establish a sustainable presence, a stepping stone for deeper exploration of the solar system. The plans include a lunar gateway, a space station in orbit around the moon that would serve as a waypoint for crews traveling to and from the surface. They include habitats on the lunar South Pole, where water ice could provide drinking water, oxygen, and rocket fuel. China has also announced ambitious lunar plans, including a research station near the South Pole, developed in partnership with Russia and other nations. Private companies like SpaceX and Blue Origin are developing landers and rockets capable of carrying cargo and crews to the moon. The lunar economy, once a fantasy of science fiction, is beginning to take shape. Companies are exploring the possibility of mining lunar resources, manufacturing products in the low-gravity environment, and even offering tourist flights around the moon. The challenges are immense. The moon is a harsh environment with extreme temperatures, abrasive dust, and constant radiation. Building and maintaining a permanent presence will require technologies that don't yet exist. It will require international cooperation, or at least careful coordination, to avoid conflicts over resources and territory. It will require sustained political will and public support over decades. But the rewards could be equally immense. A permanent lunar base would advance science, inspire generations, and position humanity for the next great leap, the journey to Mars and beyond. Moonlight is not the moon's own light. It is sunlight, reflected and softened, scattered from a dusty gray surface across 250,000 miles of space. The moon is one of the least reflective objects in the solar system, darker than asphalt, and yet it appears brilliant against the night sky because it is so close and so large. On a clear night with a full moon, you can read by its light, walk without a flashlight, see colors that are invisible on moonless nights. The world takes on a silvery quality, familiar and strange at the same time. The brightness of moonlight varies dramatically with the moon's phase. A full moon is about 9 times brighter than a half moon, and a half moon is many times brighter than a crescent. This is partly geometry, more surface area reflecting light, but also because of the opposition effect. When the sun is directly behind the observer, shadows on the lunar surface disappear, and the surface appears brighter. This is why the full moon seems to glow with an intensity that the quarter moon cannot match. moonless nights are different. Without the moon's glow, the stars emerge in their full glory. The Milky Way stretches across the sky, a river of light made of billions of distant suns. Planets shine steadily, while stars twinkle. The darkness feels deeper, more complete. Many cultures feared moonless nights as times of danger and mystery, but they are also times of revelation, when the universe beyond our small world becomes visible in all its vastness. The moon, for all its beauty, hides as much as it reveals. In its absence, we can see how small we really are. The moon's influence on Earth extends far beyond the tides. Its gravitational pull stabilizes our planet's axial tilt, keeping it within a narrow range that allows for relatively stable seasons. Without the moon, Earth's axis might wobble chaotically over millions of years, causing dramatic climate swings that could make it difficult for complex life to evolve. Mars, which has only tiny moons, experiences exactly this kind of wobble. The moon may be one of the reasons Earth is habitable. The tides themselves have shaped the evolution of life. Intertidal zones, the areas between high and low tide, are among the most dynamic and productive ecosystems on Earth. They may have been crucibles for the evolution of land life, places where organisms adapted to the rhythms of wet and dry, of exposure and submersion. The creatures that first crawled out of the sea may have been prepared for that transition by millions of years of tidal training. The moon, in a sense, helped life learn to walk. The moon also slows Earth's rotation. In the distant past, days were much shorter. Over billions of years, tidal friction has transferred energy from Earth's spin to the moon's orbit, lengthening our days and pushing the moon farther away. This process will continue until, in the very distant future, Earth and moon become mutually tidally locked, each showing the same face to the other forever. But that day is billions of years away. For now, the dance continues, slow and imperceptible, a waltz that has been playing since the solar system was young. Despite all we have learned, the moon still holds mysteries. The asymmetry between the near and far sides remains unexplained. Why is the crust thicker on the far side? Why are the Maria concentrated on the near side? Various theories have been proposed, but none has been proven. The answers may lie deep in the moon's history, in the details of how it formed and evolved in those first, chaotic millions of years. The lunar swirls are another puzzle. These strange, bright patterns snake across the surface, seemingly unrelated to any topography or crater. They appear to be associated with localized magnetic anomalies, but the connection is not fully understood. Some scientists believe they are protected from space weathering by magnetic fields. Others think they may be related to ancient comet impacts. The swirls are beautiful and baffling, patterns that nature has drawn across the moon's face for reasons we have yet to discover. There are also transient lunar phenomena, brief flashes or glows reported by observers over the centuries. Most can be explained by meteorite impacts, outgassing, or tricks of light and atmosphere. But some remain unexplained, tantalizing hints that the moon may not be as static as it appears. The moon may still have secrets to reveal if only we watch closely enough and long enough. It has been keeping its counsel for 4.5 billion years. It can wait a little longer. There is something profound about contemplating the moon. It is close enough to see clearly, to recognize its features, to feel a kind of familiarity. and yet it is far enough to be unreachable for most of human history, a destination we could dream of, but never touch. It is ancient, older than any mountain on Earth, older than life itself, and yet it is young compared to the universe, a mere 4.5 billion years old in a cosmos that has existed for nearly 14 billion. The moon is a reminder of scale. It is 400,000 kilometers away, a distance that takes light just over a second to cross. And yet that distance, so vast by human standards, is tiny in cosmic terms. The nearest star is 100 million times farther. The nearest galaxy is billions of times farther still. The universe is so large that the moon, our closest celestial neighbor, is practically in our backyard. And yet it took all of human history, all of our technology and courage, just to reach that backyard. The universe is patient. It can wait for us to grow. Looking at the moon, you are looking at the past. The light you see left its surface just over a second ago, but the surface itself is ancient. The craters you see were formed billions of years ago. The rocks that make up the highlands crystallized when Earth was still young and molten. The moon is a time machine, a window into the early solar system, preserved in stone and dust. When you look at the moon, you are seeing the universe as it was before there were eyes to see it, before there were minds to wonder about it. You are looking at the deep past, and it is looking back at you. We have spoken of the moon's silence before, but it is worth dwelling on a little longer. On Earth, we are surrounded by sound. Even in the quietest forest, there is the rustle of leaves, the call of birds, the distant rumble of wind or water. Even in a soundproofed room, you can hear your own heartbeat, your own breathing. True silence is almost impossible to experience on our planet. But on the moon, silence is absolute. Sound is a vibration that travels through matter. On Earth, it travels through air, through water, through solid ground. But the moon has no air, and its vacuum transmits nothing. If you stood on the lunar surface and dropped a boulder, you would see it fall in slow motion, see it strike the ground, see the dust rise and scatter. But you would hear nothing. Absolute nothing. The impact would be as silent as a dream. The astronauts who walked on the moon could communicate only through radio. Their voices were converted to electromagnetic waves, transmitted through the vacuum and converted back to sound inside their helmets. They could not simply call out to each other. They could not hear footsteps. They lived in a bubble of sound, surrounded by infinite silence. Some found it unnerving. Others found it peaceful. All of them found it unforgettable. A silence so complete it changed their understanding of what silence could mean. A lunar eclipse occurs when Earth passes between the sun and the moon, casting its shadow across the lunar surface. Unlike a solar eclipse, which can only be seen from a narrow path on Earth's surface, a lunar eclipse is visible from anywhere on the night side of the planet. It is a shared experience, a celestial event that half the world can witness together. During a total lunar eclipse, the moon does not disappear entirely. Instead, it turns a deep red, sometimes called a blood moon. This happens because Earth's atmosphere bends sunlight around the planet, filtering out blue light and allowing red light to reach the moon. The same phenomenon that makes sunsets red makes the eclipsed moon glow with that eerie, coppery hue. The color varies depending on the state of Earth's atmosphere. After major volcanic eruptions, when the air is filled with ash and dust, the eclipsed moon can appear almost black, lunar eclipses have been observed and recorded for thousands of years. Ancient astronomers used them to calculate the size of Earth's shadow, and from that, the relative sizes and distances of the Earth, Moon, and Sun. Columbus famously used his knowledge of an upcoming lunar eclipse to convince indigenous Jamaicans that he had power over the moon. Eclipses have been omens, warnings, and wonders throughout human history. Today, we understand the mechanics perfectly, but the sight of the full moon turning red in the middle of the night still stirs something ancient within us. The regolith is more than just dust. It is a complex mixture of materials created by billions of years of bombardment. The uppermost layer is the finest, a powder so delicate it clings to everything through electrostatic forces. Beneath this lies coarser material, fragments of rock and glass mixed with the fine powder. The depth varies from place to place, ranging from a few meters in some areas to more than 15 meters in others. The regolith contains a wealth of information for scientists. It records the history of the solar wind, capturing particles from the sun that have been implanted grain by grain over eons. It contains traces of cosmic rays, high-energy particles from distant stars and galaxies. It preserves glass beads from ancient impacts, each one a tiny time capsule, recording the conditions of its formation. By studying the regolith, scientists can learn not just about the moon, but about the entire history of the inner solar system. For future explorers, the regolith is both a challenge and a resource. Its fine, abrasive particles can damage equipment, clog filters, and irritate lungs. The Apollo astronauts found it difficult to brush off their suits, and some reported respiratory irritation after exposure. But the regolith also contains oxygen bound in minerals, metals that could be extracted for construction, and the helium-3 that might one day fuel fusion reactors. Learning to work with the regolith, to manage its hazards and harvest its riches, will be one of the keys to living on the moon. The moon affects us emotionally in ways that are difficult to quantify, but impossible to deny. There is something about moonlight that changes the mood of a landscape. Familiar places become strange. Shadows deepen. Colors fade to silver and gray. The world takes on a dreamlike quality that invites contemplation and introspection. Many people report feeling more reflective or emotional under a full moon. While scientific studies have found little evidence for lunar effects on human behavior, the subjective experience persists. Perhaps it is simply the power of beauty. A full moon rising over the ocean, or hanging low over a city skyline, or illuminating a snowy landscape. These sights stir something deep within us. They remind us that there is more to the world than our daily concerns, that we are part of something larger and older and more mysterious than we can fully comprehend. The moon has been a companion to lovers and a comfort to the lonely. It has been a source of hope for prisoners and a guide for travelers. It has been there for every moment of human joy and sorrow, indifferent to our struggles, but somehow present nonetheless. Looking at the moon, we are connected to every human who has ever looked up at it, across all of history, across all cultures and continents. The moon unites us in a way that few other things can. The tradition of naming lunar features began in the 17th century, when astronomers first